Hi everyone, welcome to the fourth lecture of this final module on sensors for healthcare. We are discussing the course on microsensors and nanosensors, and in the previous class we discussed about ECG. So with this we have covered two important sensors in the healthcare, that is glucose sensors and the ECG. Okay, two more sensors or two more techniques to measure tissues or some other important elements in a body. We thought that we will discuss two important things, that is MRI and pulse oximeter. Okay, so in today's class we are going to discuss MRI and pulse oximeter in very brief. Okay, so MRI is, we know that magnetic resonance imaging, and we have seen some people going for MRI. That can be for different purposes, like ECG was explicitly for the heart or cardiac related issues, but MRI, we know that it can be done for other parts of the body. It's kind of imaging. So let's try to understand that how this imaging is done using magnetic resonance. Okay, so if you see, MRI is a imaging technique that employs magnets, radio frequency pulses and different coils to create detailed image of the internal organs or certain tissues. Okay, so if I talk about MRI, it doesn't utilize any ionization radiation. Like X-rays, CT scan, they uses certain ionization radiation, but MRI is different from that. It doesn't require any ionization or ionizing radiation. Okay, and it is explicitly based on the principle of NMR, which is the nuclear magnetic resonance. And if some organic laboratories around you, you might have seen people taking organic molecules for NMR. Okay, exactly the same principle is utilized by MRI, but of course for body organs. Okay, so NMR is a simple technique on nuclear magnetic resonance, and although it looks very simple, but require a lot of skills. Okay, so this is based on spin, as the name suggests. Okay, we know that many nuclei have spin and they are electrically charged. Okay, nuclear spin arises from the intrinsic angular momentum of protons and neutrons, which both having a spin of 1 by 2, and when they combine inside the nucleus. Okay, so there are certain rules where the molecule will have certain spin or spin will be 0. Okay, so if you have even number of protons and even number of neutrons, we call it even nucleus. In that case the spin is 0. Examples are carbon or oxygen, carbon 12 and oxygen 16. Okay, and all nucleons here in these cases are pair off, and therefore they cancel out their spins. Okay, so in case of odd number of protons and odd number of neutrons, we call it odd nucleus, spin is not 0. Okay, and a good example can be a deuterium atom. Okay, similarly for odd number of protons or neutrons but not both. Okay, spin is again not 0, and example is like hydrogen or fluorine. Okay, and the MRI utilize exactly these molecules. It's like hydrogen inside the body. Okay, so the basic principle of NMR is when these elements are placed in an external magnetic field, nuclei align with or against the field. Okay, and radio frequency pulses causes transition between energy levels. So at this point you can say that these molecules are at excited state, and it resonances, basically it resonances with the external magnetic field. So say the molecule is placed in a oscillating magnetic field, and the molecule itself will have certain oscillation, and when these frequencies matches, we call it at resonance frequency. And the when the RF pulse is stopped, okay, the absorbed energy is emitted corresponding to specific frequency, which is detected by the NMR instrument. Okay, as I have mentioned that exactly same phenomena is utilized in a MRI. So we know that our body is made up of different fluids, different molecules, including the hydrogen molecule, and the MRI utilizes the hydrogen molecule present, or hydrogen atoms present in the body. Okay, and this hydrogen molecule is mainly coming from, say, fat or water content or other fluids content in the body. Okay, each proton acts as a tiny magnet, and when it comes in the vicinity of another magnetic field, it aligns itself. Okay, so so MRI delivers a radio frequency pulse at a specific frequency, and this particular frequency is known as the Larmor frequency, and this RF pulse tips the aligned protons out of position, or it excites them, and we call it excitation. Okay, when the RF pulse stops, the protons realign with the magnetic field. Okay, and they return to their original position, and in this transition they emit certain wavelength of electromagnetic signals. Okay, and these signals are exactly received by different coils. They are known as receiver coils. Receiver coils are basically placed around the body, which detects these emitted electromagnetic signals. Okay, so there are different kind of receiver coils placed in the body. In the MRI tool, okay, you have surface coils, which is for specific part of the body, say for example to detect certain tumor or some other tissue in knee or wrists. Okay, and they have a high SNR near the coil. Okay, then we have phase array coils. They are basically multiple small coils combined to enhance the signal coverages, and this has become an integral part of the modern MRI tools. Okay, then we have volume coils, which encircle the whole region like the head or the body, and is used for both transmit and to receive. Okay, then you have other dedicated coils tailored for specific anatomy of, say, heads or spine, and specifically based on it their names are derived, like head coil, the spine coil, breast coil, cardiac coil, or the knee coil. Okay, so this is just one type of coil. We call it receiver coil because it is mostly receiving, except one like a volume coil which can transmit as well as which can receive. Okay, so along with this we have other coiling system in a MRI tool, like you have a main magnet coil itself. Okay, which can produce a large static magnetic field of the order of, say, 1.5 to 3 Tesla. Okay, and they are basically the main part of this MRI tool, which helps in aligning the hydrogen nuclei, which is basically the proton used here, okay, in the patient's body. Okay, the second type of coil is the gradient coil, which is used for the spatial encoding. Okay, and they produces varying magnetic field encoding the spatial information for basically the image formation, because the ultimate output is the images. Okay, and then you have the transmit coil, which function as a RF excitation, and it can generate the radio frequency pulses which excite the hydrogen nuclei present in the body. Okay, so the basic steps in image formation, I think, must be clear to you, that how MRI uses magnetic resonance for imaging the different type of tissues or internal organs. Let us quickly overview whatever we have talked, and whatever system parts we have seen, including the different coils, including the other systems of the MRI, okay, or other components of the MRI. Okay, so what happens is the patient enters into the scanner, something like this. Okay, the patient here is entering inside a scanner, a big scanner. Okay, and when he enters into it, because of the static magnetic field, the protons in his body, okay, it can be in the body fluid or in the fat or in the water content in the body, align with the strong magnetic field which is being created here. Okay, now in the second stage, the RF pulse tips the proton, causing them to move out of alignment with the magnetic field. Okay, the third stage is when you stop actually the RF magnetic field, RF pulse, and you allow these protons to relax. Okay, so when proton for relaxing, it was at resonance frequency, okay, or it was at resonance, and it starts emitting electromagnetic signal, okay, during the relaxation process from the excitation. Okay, now the fourth stage is the gradient coil modulate the field to encode the spatial information. We have just seen the use of gradient coil. Okay, now further in the final stage, the received signals are processed to reconstruct a detailed images, and this is received by the receiver coils that we have just seen. Okay, so basically all the MRIs are done in this way, but then there are multiple types of MRI, specifically focusing on what kind of images you want. Okay, so depending on what kind of diagnosis you have, there are two fundamental type of MRI image contrast that highlights different tissues based on their physical properties. Okay, so you have a T1 weighted MRI and T2 weighted MRIs. Okay, so the T1 weighted MRI images are produced using specific radio frequency timing sequence that make fat appear bright and water appear dark. Okay, so in the process, your fat is appearing bright and water or other fluid part in the body is appearing dark. So the T1 image are actually utilized for visualizing anatomy, where fatty tissues like what matter in the brain are bright. Okay, so this helps in distinguishing fine structural details in the fat, and also it helps in distinguishing parts from the fat from the water or other liquids in the body. Okay, the T2 weighted MRI image are created using a different timing that highlight water. So both fat and water look bright, but water and fluids are actually very bright. Okay, in this case, in the T1 case, you have seen that fat only appear bright while water and fluid appears dark. But here in the case of T2 weighted MRI, both actually looks bright, but then water and fluid are actually very bright. Okay, so this type of image are ideal for detecting some pathological condition, so that you can of course distinguish between the fluid and the fat, but at the same time fat is also highlighted. It is not in the dark, so it is also bright, but then the fluids images are brighter, so it stands out among the two. Okay, so the applications of this MRI are tremendous. So they can be used for brain or spinal cord imaging. Very rare, I mean it's not possible by other imaging without using the hazardous ions. Okay, so here you are not using any kind of hazardous material. Of course, sometime you have to introduce some gadolinium and other things, but we are not discussing that right now. Okay, then it can also help in analyzing joints and soft tissues injuries in the body. Okay, they are very helpful in identifying tumors, infection, and the vascular diseases, and they are also suitable for cardiac and abdominal imaging. Okay, their advantages are again they can give you excellent contrast of the soft tissues. Okay, and no ionization radiation is involved here. Okay, multiple imaging planes are possible in the MRI because your fluid is basically, or the fat is basically distributed in the 3D structure of the body. So multiple imaging planes are possible. Okay, the limitation of these devices or this technique is they are expensive and require long scan time. Okay, they are not suitable for patient who is carrying certain metal part in the body or the pacemaker, because in the external magnetic field this conductor will start inducing a magnetic field. Okay, so even if you have seen someone going for a MRI scan, his pockets are thoroughly checked for any coins or other things. So usually these things are avoided. So anything ferromagnetic objects, if by chance if he carries, it can be dangerous for his health. Okay, so So although they have certain limitations, but then MRI is very popular for this tissue imaging. Okay. Then another simple sensors that we have seen, particularly it has seen a rise in the COVID time, is a pulse oximeter. Okay, we have seen people clipping kind of small device on our fingertips to calculate the saturated oxygen level. Okay, so the pulse oximeters are a small non-invasive device that measures oxygen saturation in the blood. Okay, and it can monitor the percentage of oxygen bound hemoglobin, we call it SpO2, and they are based on the principle of mostly spectrophotometry. Okay, so they basically utilizes two different wavelengths, red light and infrared light. So red light of the order of 660 nanometer, and infrared of the order of 940 nanometer. Okay, so in the body, in the blood, the oxygenated and the deoxygenated hemoglobin absorb these lights differently. So their absorption phenomena is their absorption pattern is actually different, and based on this, this pulse oximeter actually works. Okay, so when you clip this pulse oximeter on your finger, okay, it passes these two wavelength lights, and at the other end you have a photo detector which measures the transmitted light. Whatever has been absorbed by the blood, it takes into account, of course. Okay, so basically the ratio of the absorbed red and the absorbed IR, so 660 nanometer absorption and 940 nanometer light absorption ratio is calculated, and it calculates the oxygen saturation using the popular Beard-Lambert law, which we have discussed in more detail in our previous lectures. Okay, so these pulse oximeters can differentiate between pulsatile arterial blood from other tissues by varying the absorption, and it correlate with the heartbeat. So you must have seen that these SpO2 meters not only tell you the SpO2 concentration, but it also relates to the heart pulses. Okay, so output of these pulse oximeters are mostly in the form of SpO2 percent and the pulse rate. Okay, and if you see the application of these pulse oximeters, although they are very cost effective and small non-invasive device, they are very useful in monitoring oxygen levels in patients with respiratory or cardiac conditions. Okay, and they are very standard devices, and they are thoroughly accepted in all the clinics and hospitals. So you might have seen it in the ICUs, emergency rooms, and even in the operation theaters. Okay, they helps in assess different lung diseases based on the SpO2 conditions like COPD, asthma, and pneumonia. Okay, it also distinguish between different heart conditions. Okay, they can help in assessing the effectiveness of supplemental oxygen if the patient is on certain medication or on oxygen ventilation. Okay, it can also help in diagnosis of sleep apnea. Okay, and it also helps in surgical and sedation monitoring. Okay, the normal SpO2 levels in a human body is around 95% to 100%. Okay, so below 90 to 92% can indicate that there is a need of supplemental oxygen, and it has to be monitored continuously to guide treatment decisions. Okay, so therefore you might have seen that in the critical unit, mostly the clips are always on. The patient is always wearing a SpO2 monitor to monitor the oxygen saturation level. Okay, because it can we have just seen that it can tell you about different health condition. Okay, these devices are non-invasive and painless, therefore they are very suitable for calculating this SpO2 percentage. Okay, they can give you immediate and continuous result. Okay, so continuous monitoring of SpO2 level is possible. Okay, they are very much portable, very small device to carry. okay, and useful for clinical diagnosis, as well as they are equally capable at our home diagnosis, so kind of point of care device, okay. However, they have certain limitations, like they are affected by poor circulation. If you have skin pigmentation, or you have kind of nail polish, it may get distracted, and its result can be sometime erroneous, okay. They may give inaccurate result in case of abnormal hemoglobin conditions, okay, and they cannot measure oxygen metabolism, or it cannot give you CO2 concentration, okay. So that's all about pulse oximeter. So till now we have covered four different sensors working on different principles, okay, for healthcare monitoring. They are glucose sensors. We have given considerable amount of time to discuss the glucose sensors, okay. Then we have talked about ECG sensors, okay, or ECG devices. Today we talked about two important devices for healthcare. They are MRI imaging tool, and another is a simple pulse oximeter. But these are not exclusive list for sensors in the healthcare. Okay, there are a number of other sensing devices which are being utilized for healthcare monitoring, okay. Say for example, like say PPG, okay. PPG sensors measure heart rate and oxygen by light absorption. Similarly, you have EMG, EEG for muscle activity from skin monitoring, and brain electrical activity from the scalp monitoring, okay. You have blood pressure monitors, okay. Then for respiratory rate monitoring, you have a number of devices like chest belts and wearable mask kind of devices. And for imaging, again, you have a number of devices or number of techniques like CT scan, X-ray, then you have ultrasounds, okay. So these are again these are not the complete list of healthcare sensors, okay. But once we have understood these four different kind of sensors, okay, glucose sensors, ECG, MRI and pulse oximeter, it will definitely assist you in understanding the other techniques. Like if you talk about EEG, again it is kind of electrode based devices, okay. If you talk about any other biosensor to monitor certain kind of pathogen, for example, or other molecules in the blood or in the tissues, okay, mostly you rely upon electrochemical sensors that we have covered in more detail in the glucose sensors. So please note that the electrochemical sensor or the optical sensor that we have discussed is not exclusive for glucose monitoring. Of course, we have seen in the context of glucose, because we are using different enzymes explicitly utilized for the glucose monitoring. But then if you modify it with different class of antibodies, it can be helpful in monitoring different antigens in the body or in the interstitial fluids, okay. So with this, we are finishing this healthcare sensors. In the next class, which is our final class, we will just summarize. We'll see what topics we have covered, what we have learned over the 59 classes that we have covered, okay. And we'll try to summarize that what could be a takeaway from this course, and what else we can study to supplement the knowledge that we have gained over the 59 classes in this course. Thank you.